All right, welcome back to operating systems. So this lecture will be slightly confusing, but that's okay. You actually don't need to take that much away from this lecture. We'll be figuring out how stuff actually works, and it will hurt a little bit, but I'll point out what you actually need to know. For the most part, this is mostly like how things actually work, and it's okay if this is a little bit confusing, but it should be mostly understandable. So again, feel free to ask questions. So this is our Hello World program I alluded to last lecture. Let's just go verify that it actually works. So if we go and execute it, prints Hello World. That's what we expect. That's Hello World. It's just really, really small. So as a first aside, you don't really have to know this, but it might help you whenever you look at stuff and try and understand stuff. So there's three major ISAs or instruction set architectures today. You'll probably touch all three of them at some point in your life. So it's machine code or numbers the CPU understands. So your assembly code is really, really close to this. It's just a human representation of machine code, just so you can read it a bit better, even though it's probably not that readable. So the three architectures are x86 64-bit, and that is like desktops, non-Apple laptops, computer or servers, like most things running in the cloud, things like that. Then there's AArch 64, which is called ARM 64, and that's, if you're lucky enough to have an Apple laptop, that's what it's running. Your phones are going to be running that architecture, tablets, things of that nature. Your computer organization course, that was some flavor of ARM, so it's used for things like that. So there's another one that you might not have seen yet called RISC-V. It's basically an open source implementation of ARM. So you can actually implement your own RISC-V processor if you want without having to pay X million dollars, which is kind of nice. So we'll be looking at a kernel that uses RISC-V in this course, but if you can read ARM, we can read this and we won't really have to read that much assembly anyways. It basically looks like an ARM processor. But again, we'll touch all of them in this course. It's good to know them. Won't test you on this. So our next abstraction that we alluded to before is something called a file descriptor. Because why do we even have something called a file descriptor? Well, we discovered before all our processes are independent. And if they're all truly independent, that means they're all truly worthless because we can't read anything from them. We can't see what they're doing. We can't get any information out of them. A truly independent process is completely useless. So since they're independent, we need an explicit way to transfer data, and that's where file descriptors come in. And this is a type of something called IPC, which is one of the core things an operating system has to do. And IPC stands for inter-process communication. What that means is basically you just want to communicate between two different processes that are running. They don't even have to be running at the same time. So anytime you transfer data between two processes, that's IPC, inter-process communication. What a file descriptor is, it's a resource that users may either read bytes from or write bytes to. And it is identified by just an index, and that index is stored as part of the process's information, and the actual index is independent to that process. So if you open a file and you get file descriptor 3, and that represents your open file, as long as you don't close file descriptor 3, for as long as your process runs, file descriptor 3 will represent that file. No one else will monkey with it. So for now, a file descriptor could literally represent a file, which probably makes the most amount of sense to you. But because it's abstract, it's only something we can read bytes from and write bytes to, well, it could represent pretty much anything. So it could also represent a terminal. So what you type in, that could be writing bytes to it, or sorry, reading bytes from it, and then whenever it's displaying output, well, the process is writing somewhere, and then you can see whatever it writes. So next we have to get into system calls. You do need to know system calls, just not how they're implemented. And we'll explain throughout this lecture what a system call is. That's like one of the main things you'll take away from this lecture. We're going to go over it like 1,000 times. So system calls are a way to make a request to the operating system itself. So they can kind of look like regular C functions. You can think of them that way, but they're a bit different. But if we think of them as C functions for now, let's just kind of explain two of them. So the first one is called write, and that writes bytes to a file descriptor. So it has three arguments there. The first argument, FD, that's the number representing the file descriptor to write bytes to. And then the second argument, that buff, is the address at the start of a byte array. So you just give it a big array of bytes. And then the last argument, count, is how many bytes to write from that array. And what it returns is the number of bytes actually written to that file descriptor. So if it can't do anything, it might return 0, even though you say write a bunch of bytes to it. Or if you say write 10 billion bytes to it, it might be like, no, I'll write 1,000 instead. And then you could do another write system call if you want. Just depends. And the reason that you see size t and s size t as the return type. Well, s size t is just a signed size, which just means it can go negative. So if write returns negative, it means there's an error. Then the other system call is called exit group, and it takes one argument called a status. And what that system call does is exit the current running process and then sets some error code. So the exit status is just a number that you can use to represent whatever. Usually the common convention, 0 means your program exited without any problems, which is why you return 0 from main. That just means nothing went bad. And if something went bad, you return something other than 0. You'll see here that the only valid values are 0 to 255, which is 1 byte. So the argument's an int. So if you use a bigger number, it'll just get rid of all the more significant bytes and only keep the least significant byte. Do you need to know that? Not really. But it's how it works. So to explain the hypothetical hello world program, those are the system calls we need. But I also need to explain a convention. So there's a convention between every single process running on your operating system. At least if it's Mac OS or Linux. Windows does weird things. But by convention, whenever a process starts, there are 3 valid file descriptors. File descriptor 0 is supposed to represent standard input. So that's where you read bytes from, if it's a file descriptor. If you used C and you took user or input from a user, and it was called standard input on Linux at least just means it's reading from file descriptor 0. It's just a convention, and it would represent your terminal most of the time. So the standard C library will make dealing with it a bit easier, and you might be able to get an integer out of it or something like that. But at the end of the day, it's just doing some work for you. It's just reading some bytes from somewhere. Then the next two, one is standard output. So that's where it's expected that anything you see on your terminal, you'll see that's normal output. So normal output goes to file descriptor 1. So if you have printf, it actually goes to file descriptor 1, again, on Mac OS or Linux. Then there is file descriptor 2. That is meant for standard error. The convention is anything you write there. Most of the time, your terminal, you can't tell the difference where the output's coming from. But if you want to be nice, and we'll see why it's kind of useful in a little bit, if any error happens in your program, you write your error messages to that file descriptor. So some of the built-in C functions will actually use that file descriptor to write errors for you if you've used them. Hopefully you've checked for errors. In this course, you will want to check for errors because you will figure out that literally everything your computer does can fail. And yeah, you'll probably want to check for errors. So the most basic hello world program, if we assume C didn't exist and main didn't exist, and we could just magically define a function. Here the name doesn't even matter, but we could just define a function that doesn't return anything and doesn't take any arguments. And if we could magically have our computer start executing this function, this is all it would need for hello world. It would need a write system call to file descriptor 1, because it's hello world, I'm just writing the standard output. Then I would need the address of this string, so hello world with a new line character. And then how many bytes to write. So I'm going to write 12 bytes. Why is it 12? Well, pretty much every character is 1 byte. So hello is 5 bytes. Space is another byte. That gets us to 6. World is another 5. That gets us to 11. And this \n, that's actually a new line byte. So that's actually 1 byte, which gets us to 12. So if magically I could just start executing this function, this is all I would need for hello world. And it's just by convention of those file descriptors. So another quick aside. So you've probably heard of an API before, I hope. So, but in this course, we don't have to know the ABI, but it's going to be useful to have some background with what that means. So an API is like very high level. It tells you what to do. An ABI stands for Application Binary Interface. Is like the real low-level details that hopefully you never have to see outside of computer organization and this course. So API, it's like Application Programming Interface. Abstracts the details. It's just supposed to describe what the function does, what arguments it takes, and what it returns. So like a function takes 2 integer arguments and it returns an integer that's supposed to be the addition of them or the multiplication of them or something like that. It's like very high level description. I'm not telling you registers or anything weird like that. But an ABI or the binary interface will tell you in gory details exactly where everything goes on that specific CPU. So that function would have an ABI. So I could say, hey, to make a function call to this function, I have to use the C calling convention. So that's an ABI. Basically, without getting into the gory details of that, it passes arguments on the stack. In your computer organization course, you probably passed arguments in registers, right? Everyone remember that? So remember when you made function calls in that course, you passed arguments in registers, and then you had to make sure they lined up on both sides of the function call. And that was all fun. So that would be an example of an ABI. So it's a contract between the function that says this value has to be in this register. Otherwise, if it's not there, it's not going to work. So to make requests to the operating system, you can't just call functions. So there's no functions to the operating system. So the only way to make requests to the operating system is through a function call. And because there's no address or anything, the way you make system calls on every single operating system, again, now this is like includes Windows, is you generate an interrupt. And there's a specific CPU instruction that will generate an interrupt to the operating system. So you've dealt with handling interrupts in that course, so you can imagine what the operating system has to do. But now you are generating interrupts yourself. Although you never, aside from this one example we'll see, you'll never generate your own interrupt. Actually, that's not true. But for the most part, we won't do it in assembly. So specifically on ARM, to generate an interrupt, there is this SVC instruction, and that will generate an interrupt. And in order for the operating system to handle your system call, well, there needs to be some type of calling convention. It's like the same thing you had in that organization course. So there's some registers that are defined to be some things. So the X8 register is just a number that's representing what system call you want to make. So if you want to make a write system call, it's a certain number you can look up. If you want to make exit group, it's another number you have to look up. And then you can have up to 6 arguments, and they are passed in registers X0 to X5. So can anyone think of any limitations of this ABI? Yep. Yeah, I only have 6 arguments. How many arguments can I have in C? A lot. Until my stack wears out, pretty much. So any other limitations for this? Yep. Oh, so that was, it's slow. Technically, passing registers is really fast. Sorry? Oh, the interrupt is slow as hell, yeah. But yeah, just in terms of passing things in registers like this. So any other limitations? Yep.
Your arguments have a limited size based on the register, how big the registers are?
Yeah, all the registers are the same size. So if all my arguments don't fit in exactly a register, I might be wasting space or I won't have enough space. So they're all a set size in C. You can pass ints, you can pass doubles, you can do whatever, and it's fine. So those are two limitations. It's good to know those limitations. You do not have to know, all you have to know here is that it passes things in registers. You don't have to know the specific register numbers. It's only going to be for this example. All right, so the next thing we need to understand is that programs on Unix use the ELF file format. You will never be tested on file formats. This is just so we can explain that hello world program, so you can relax. So, like I said, the ELF was a coincidence. It actually stands for executable and linkable format. Has nothing to do with me. And it specifies the file format for both executables and libraries. And like we saw before, it always starts with the same 4 bytes, and they're literally called magic. The more you learn about computers, the more you realize that magic is just random numbers and knowing what those random numbers are supposed to be. At the end of the day, that's like literally all of computing. Machine code is just magic numbers. Strings are magic numbers that mean something if you know how to decode them. Everything's just a magic number. And there's a whole list to see that I'm not lying. It's like the file format for everything. You can look at the Wikipedia list. So if you want to explore PDF files, everything's going to start with that ampersand, not ampersand, sorry, percent sign PDF and a dash, every single PDF file. So the bytes I showed you before for that Hello World program, what they actually represent that we know is they represent an ELF file. So this ELF file, what it has to do is tell the operating system what to do with it, and it also contains the instructions of data. So basically, all that file does is to say, load this entire file into memory, starting at address 10,000 in hex. Why 10,000? Well, memory is virtual. We can pick any number we want. Some are reserved, so we can't pick starting at 0, because 0 is, by definition, some invalid memory. And that's why if you dereference null, you get an error and all bad things happen, so you can't do that. But otherwise, we could actually tell the operating system to load this program at any old address we please, because this is all virtual memory, and we just have it figure it out. But in the specific thing I wrote, it's address 10,000 in hex. So there's 2 parts of an ELF file. It always has to start with a header file, which is 64 bytes, which is like almost a third of that file. And then a program header, which is 56 bytes. So all this information to tell the operating system about our program is 120 bytes, which is most of our program. And again, you don't have to know about ELF headers or anything like that. So the next 36 bytes in that binary file actually represents the machine code for the actual instructions to make some system calls. So there's 36 bytes in instructions, and then after that, there are 12 bytes that are supposed to represent the string hello world. So if we load this entire program into memory at address 10,000 hex, and these 2 headers take up 120 bytes, well, if we need the memory address of where our instructions start, it is at the 120th byte is the first byte of the instruction. If you convert that to hex, it is 78. And then because the file, we told it to load it at 10,000, we just add it to 10,000. So the instructions would actually start at address 10,078. And then the string is going to be after the data in this program. So it starts at address 10,009C because the string is after all of the instructions. So it would start at byte 156, which is 9C in hex. So the string would start there. This is like gory detail. You don't have to know that, but this is like what the operating system has to understand. If you want to go into the gory details, which I don't recommend, but hey, you're all adults. I can't tell you what to do, except I can, kind of. So I guess I set labs and stuff like that in exams, but I can't tell you what to do on your free time. But so if you want to see all the gory details, you can use that. We'll just skip that. So visually, how it looks is that first 64 bytes are up here in the blue in the file header. It specifies a few other things. So it begins with that elf. And then if you know which bytes to read, it will describe the endianness, so little endian or big endian, the instruction set architecture that this file is supposed to run on. So that way your operating system knows what ISA it's running and can read that information. And if it doesn't match, it means it can't execute it, so it doesn't even have to try. It can just bail out. The next is the entry point. The entry point tells the operating system where to start executing from. So in this case, if our instructions start at this address, this would be our entry point for this program. And whenever the kernel starts executing, it would start executing at that address, which is good because that's the beginning of our instructions. And this is what the operating system cares about. So you might have heard that, hey, in C, execution begins at main. That's a lie. It begins wherever this tells it to begin, and if you compile a C program, it's not main. So sorry for that. But we'll figure out what C does in a little bit. Okay, so all the bytes in cyan basically tells what to load into memory and where. And this is where it just says load everything at address 10,000 hex, and it wastes a bunch of bytes for that. And then we have our instructions, and then our data. So those bytes that represent the machine code, so you might actually do some of this stuff if you get into like cybersecurity or like, you want to hack stuff or do other fun disassembly stuff or see how programs are actually made. You could actually just take the bytes and put them into a disassembler. And if we do that to these bytes, these are our disassembled instructions. And they look similar to how system calls are being made because these are supposed to represent system calls. So it's okay if we forgot already, but X8 is the register where you put in the number of the system call you want to make. So if we want to do hello world, we want to do a write system call first. And it just so happens that the write system call is 64. And then the first argument is a file descriptor. We want to write to file descriptor 1. Then the next is the address of the starting address of the string. So that was at 10,009C. So because it's ARM, we have to do it in two parts. So we have to load the lower bit or lower byte of X1 with 9C. And this just adds 10,000 to it to get the address we expect. Again, don't have to know this. This is just some ARM crap. And then the next argument is the number of bytes to write. And here we just write 12. So that's how many bytes are in our hello world string. And then we have this SVC instruction. Then that will generate an interrupt. The operating system gets to do the system call. And whenever the operating system is done with the system call, it will just continue executing your program after that SVC instruction. So after it's done the write system call, it will do this instruction. So we're going to do a different system call. We want to do exit group. It happens to be number 94. And then the argument we give it is 0. And then we do an SVC instruction. So that does another system call. And because it's exit group, our process is dead now, and it can't execute anything, so it doesn't exist anymore. And the rest of the things are 12 bytes for hello world of the string itself. It's ASCII encoded, and for some reason, or just as a fun to know, whenever they made the ASCII standard, they made it really easy to tell whether a character is an uppercase or a lowercase number by looking at a single bit as like an optimization. So if you want to check if something's an uppercase, you check bit 5. If it's 0, it's uppercase. If it's 1, it's lowercase. It means the values differ by 32. Why I'm telling you this, I don't know, but hopefully it might be useful to one of you at some point in your life, but probably not. So that's every single byte. So we load the program in, we tell it where to start executing, we just have a few instructions, and we have a string. And before I even start executing, can you already tell a difference between the string I used and like a C string? So what is a C string? Oh, way back there, yeah. Yeah, the null character. So the null character at the end of a string is literally just a C convention. Your operating system doesn't care. So that's literally just a thing in C. And we'll see that as it goes on and why that might make sense. Okay, so this is also an important part, and this is also Captain Obvious. So, well, it will be Captain Obvious in the next slide. So the kernel is a core part of your operating system. You probably heard the term kernel before, but you might not know what it is. So on your CPU, there's a special privilege mode called kernel mode. And if your CPU is, it's just basically a switch. And if your CPU is currently in this kernel mode, it can access more instructions. So it can access special instructions that can directly communicate with the hardware. Depending on your architecture and whoever made the CPU, they might call kernel mode something different. On RISC-V, it's called S mode or supervisor mode. I believe it's called the same thing on ARM. On x86, the old processors, it's called ring 0. So it might be called different things, but the generic term for it is called kernel mode. That's the term we'll use in this course. And this is the Captain Obvious part, is the kernel is the software or the part of your operating system that runs in kernel mode. So if it's software running in kernel mode, it's part of the kernel. It's kind of like just a big tautology there. So again, kernel mode instructions, they're the only ones that are allowed to directly interact with hardware. So this means, for example, any instructions. Whoa, that was aggressive. Okay, that door is heavier than I thought. My bad. I didn't try and be that aggressive. Whew. All right, so for example, in supervisor mode or kernel mode, you can access instructions that will let you play with virtual memory and reconfigure virtual memory, which you don't want your application to do, because if it could, well, then it could probably reconfigure virtual memory to read other processes' memory, and then suddenly they're not independent anymore. So the kernel has to manage that, and there has to be like actual hardware privileges so that there's no way that any application, there's like a clear separation so that no user application can change it. So this is kind of how it looks like on a modern CPU. So this is as complicated as privilege modes get. So where you've been at so far in like anything you've ever written in like any C program, so like 105, that code is actually executing in something called user mode or U mode on RISC-V. And those are the least privileged instructions. So if you try and execute an instruction that tries to interact with hardware, the operating system won't let you do it. Then there is S mode or supervisor mode or kernel mode, which is where your kernel exists. And this is the core part. So there's a kernel as part of macOS. Linux is actually the name of a kernel, not an operating system. And on Windows, Windows will also have its own kernel. Then as you get more complicated, there is an H mode for hypervisor mode, because virtual machines, while they need to be independent, so there needs to be something to manage virtual machines. And that is something called a hypervisor, which we won't have to know until the very end of the course. But that's what enables something called virtual machines. It runs in that mode. And then at the very end, there's machine mode, which is just access to literally every single instruction. This is what you had in like your computer organization course. There was no CPU modes or anything. You could just access any instruction you wanted. There was no checks, no balances, nothing like that. You could just do whatever you wanted. So in RISC-V, it's called machine mode. It's just full access to everything. generally like really low-level hardware operates there, something we won't touch on this course. So there's only one way to get between user mode and kernel mode no matter what, and that's what system calls are. So system calls will actually transition between user mode and kernel mode. On the Linux kernel, there's only 453 of these functions. So that's the entire interface to your kernel on Linux. So there's only that many functions. Some of these we already have seen briefly: read, write, open, close. We can kind of imagine what they do. And then at the end of this course, you will know what all of these do by looking at them and be able to explain actually how they work. But for now, they are a complete mystery. You might be able to guess, but you should have no idea what the rest of these do. You could probably guess a little bit. Okay, so the nice thing about having this clear separation, where if you want to interact with the hardware, you have to go through you have to go through a kernel, and you have to do it through system calls. Because we have this on Linux, you can actually trace system calls using a command called strace, and it will tell you what literally any program does. Since every program has to interact with a kernel, you can tell no matter what language it's written in, no matter even if it's not written in a language, if it's just some psychopath writing in bytes like what I did, it will tell you what the hell it's doing. So we can use this program to see what our hello world problem does, and hopefully it makes those two system calls. So if I run strace on that, well, I can see, so first off, this line doesn't count. We'll figure out what did this and where this came from, but this is not what we did. But we can see it's a little bit jumbled, but it looks kind of correct. We wrote to file descriptor 1, hello world 12, and then we actually see the hello world line we writ itself. So they're kind of jumbled together here. And then we have the rest of the trace that says we did an exit group. So this is where, so strace actually writes everything to file descriptor 2, standard error. So if we wanted to get rid of what strace is doing on Mac OS or Linux, you can do this. What this means is take file descriptor 2 and redirect it somewhere. So instead of going to your terminal, I can tell it to go to the special location where it just deletes everything. So it just kind of goes off into the void and no one ever sees those bytes again. So if I do that, I won't see any output from strace. And if I go ahead and change that from a 2 to a 1, then I won't see hello world anymore, and I'll only see strace. So if I want to see it a bit cleaner, I can do something like that. So my hello world program, it does a write system call, file descriptor 1, standard out, hello world, exits. That's it. That's hello world. So let's see what C does. So above there, I have hello world in C. Everyone agree that that's hello world? It's the hello world everyone has seen before. So if I compile it, so it's already compiled. So my program is 168 bytes. Anyone want to guess how big the C version is? Any guesses whatsoever? Throw them out there. Kilobyte, we got a kilobyte. 5 megabytes, all right. Someone thinks we're writing JavaScript. All right. So if we got 5 megabytes, we got a kilobyte. Let's see. Build. So the size is right here. So it's 70K, which is 70 times 1024. So number of bytes. So it's pretty big. So it must be doing some special stuff. So if we strace it, well, first let's execute it to make sure it works. So it prints hello world. Doesn't seem to do anything different. So if I want to see what it's actually doing, what should I use? strace. Yeah, I can see what it's doing. So let's get rid of the output. So if it's doing just hello world and nothing else, it'll just be write, exit. That's it. So at the end, it did write, exit. So it did hello world. It did some other things too. So even without knowing what it's doing, let's see if we can take a guess. So this means nothing to us, hopefully. Oh, you have a question?
Just say, is some of that stuff at the start probably include of the standard?
Oh, so the question is if some of this is doing the include? Is that what you think some of this is doing?
Or rather, it is the include stuff, but is included when the compiler sees it.
No, so when your C compiler, so when it's compiling, it will use that include, but your executable won't have an include or anything. That's just so it knows how to compile things. So this include specifically will just have like the function arguments for printf, and that's pretty much all we need from this include. So yeah, it's a good guess, but that's not what it's doing. When it gets compiled, that doesn't exist anymore. All right, let's see if we can guess. So BRK means nothing to us. Most of these probably won't mean anything to us. mmap means absolutely nothing to us. We couldn't guess. F-access at means not that much to us, but that kind of looks like a file path. That kind of looks like a file. So some cache. It's using some cache. I don't know. Caches are good. Caches are fast. So that's probably good. More stuff we don't know. This one is interesting. So here, it's C. That looks like libc. So that's it loading your C library. So if it's using C, it's going to use the standard C library. So it has to load it at some point. So if we get to monitor everything it's doing, well, it should do something with the standard C library. So here it's opening the standard C library, and then it's reading from it. And we can tell that the standard C library is just an ELF file, like I said before, because it starts with ELF and that magical byte. So we saw before that that byte in hex is 7F. This is actually 7F. For some reason, I don't know why, this is an octal. So that number is an octal. Don't ask me why, but 177 in octal is the same as 7F. Anyways, so it has to open the standard C library. It reads some information from the standard C library. Then it does some magical stuff that we don't know. So mmap, we'll get to it in this course, but that's basically requesting the operating system to monkey around with virtual memory somehow. So it's doing a lot of monkeying with virtual memory. It's doing some more monkeying around that we don't understand. It did some ioctal, but got an error inappropriate, so it was very inappropriate. So that's probably not good. Who knows what C is doing? And then at the last case, so this BRK is actually, it's requesting space for a heap. So this is like the start of your heap, and then this is it requesting heap space from the operating system. So that's what BRK is doing. In a more advanced course, this is what, so your memory allocator, like malloc and things like that, it uses this memory and it manages it. But it has to do system calls like anything else. And then at the end of the day, it does write exit group. That's it. So eventually at the end of the day, it did do hello world, but it took a while. But hey, because we have this strace now, we can see what other things do. So Python prints hello world. Well, we can strace Python. So if we strace Python, it does some more stuff. But at the end of the day, it does exit group. So that's the only way to exit. And then after a few things, it did write, but it did some other things in between that. And if we scroll up, well, we can see, hey, it opened that file. It had to read from that file. So it had to read my print command. So it read print. It actually read the file twice for some reason. Don't know why. But hey, you can see what Python's doing. And you can scroll up and see that it does a lot of stuff. So I ran this ahead of time. So Python does like roughly over 350 system calls to print hello world. So, for fun, JavaScript, that's a language. It's a language I hate, but it's a language. It does hello world, and you can strace it. Whoops, wrong number. So, at the end, it did exit group. Where's its right system call? Very good question. There's an unrelated write to file descriptor 14. Nice. Da 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 do do do. Can't find it, so it's somewhere there. So let's just see how many system calls Java makes. Oh, over 1,000. Nice. So you can actually get, undisputed proof of what your programs are doing, and undisputed proof that JavaScript's at least 3 times worse than Python, even for hello world. So that's fun. You can even use that for any program you've written. So you can go back to your APS 105 things, just strace them all just for fun. Although they'll probably do more or less what hello world does. Oops, code. So yeah, the system calls finding the standard library, loading it, basically what it was doing. So you can think of the kernel as a long-running program that never ends. So if you want to, like in Lab 0, when you write a bit of code that is a kernel, part of the kernel, well, you didn't write a main or anything, so it's more like writing library code. There's no main, and the kernel lets you load code into it as it's running, and then it will execute that code in kernel mode, so you will have the ultimate power to do whatever you want. So this code is just called modules because they're supposed to be kind of loaded on demand, and you can unload them on demand, and the kernel can manage them. So mostly what these are used for is if you plug in new hardware, the kernel knows what module that hardware corresponds to, so it will try and load that, and that will have all that code that will handle that specific hardware. And then if you unplug it, it doesn't need that code anymore, so it would unload it. But when you write your kernel code in Lab 0, that doesn't really do that much. If you really wanted to and you knew what calls to make, you could do whatever you wanted. You have unfettered access. Your code is actually running in kernel mode when you insert it into the kernel. So if you knew what you were doing, you could read the memory of any process you wanted to. You could just exit any process you wanted to. You could do whatever you want, right? Possibilities would be actually endless for that code as long as you knew what to do, which is why if you have code that can escalate privileges and be inserted into your kernel, well, then your computer's pretty much gone because it can do whatever it wants. Your kernel is the thing that's maintaining security. So if your kernel gets compromised, you're kind of hosed at that point because kernel code can do anything. So it's a really important part of the software stack. So there's a bunch of different architectures for the kernel that separates out what the kernel is responsible for. So the Linux kernel is an example of a monolithic kernel. So these are just little terms you should actually know. So a monolithic kernel tries to run as much as it can in kernel mode to make things as simple as possible, but it makes the kernel really, really big. But Linux is an example of that. But in this architecture, the kernel is responsible for managing virtual memory. It's responsible for managing process scheduling, which is what executes on the CPU at any given time. Responsible for IPC, or inter-process communications. It will be responsible for any file system code, so how you actually read data from a device, what formats it's structured in, and device drivers, so how to talk to a video GPU, how to talk to all sorts of controllers on your machine. There's another form of thought of that, hey, if kernel code is like really, really sensitive and you want to eliminate your attack surface as much as possible, well, we should take things out of the kernel instead of putting everything in the kernel. So a microkernel tries to run the minimum amount of services in kernel mode, and then run everything else in user mode so that if that gets hacked or if it's wrong or if it has an error or whatever, that none of that code actually runs in kernel mode, so nothing can actually touch your hardware. So what would actually be running in kernel space that the kernel is responsible for would be managing virtual memory, process scheduling, because it needs to, that has to be directly with the hardware. You can't move that out of the kernel. And then you have to have some form of basic IPC that the kernel handles so that other processes can't read other processes' information. And that is the bare minimum, more or less the bare minimum you can actually have in your kernel. And then kick everything up to this normal application code that runs in user mode. There's all types of other kernels where they split that line. So there's hybrid kernels that are somewhere in between monolithic and microkernels. So for example, Windows is like a hybrid kernel because it has emulation services in user mode because it's like the old DOS stuff. Windows also had like an HTTP server in kernel mode, which was kind of weird and a bad idea, but yeah. So Mac OS isn't quite a microkernel, but it does have device drivers in user mode, but it has other things like file systems that are still in kernel mode. But it tried to push some more stuff out into user mode than kernel mode to make it smaller. And you might argue that, hey, that's one of the reasons that Mac OS is more secure than Windows. There's also like research in this area. If you want to do OS research way off into grad school, if you want to do that, where you try and make it even smaller than a microkernel. So there's something called nanokernels and picokernels, and there's just a whole form of research that tries to make them even smaller than microkernels. But for all this, there's different lines you can draw, different trade-offs. This is engineering, so wherever you draw that line, there's no clear winner. One isn't always better than the other in any respect. So the big thing you have to know in the lecture is that the kernel, it interfaces between different CPU mode boundaries. So the kernel is a part of the operating system that interacts directly with the hardware. It is running in a special CPU mode called kernel mode. And the only way to go from user mode to kernel mode is with a system call. And that's primarily where this course is focused. We're going to be on the boundary of system calls. So we're pretty much going to be making system calls and then explaining what's actually happening on the kernel. And that's pretty much where this course lies. And the nice thing about it is no matter what language you write in, even JavaScript, every single program uses this interface. So no matter what you end up doing, if you write a computer program, this course is applicable. You can write strace on literally everything. We saw some more unimportant stuff like the file format and instructions to define hello world. That wasn't important. The difference between API and ABI, you might want to know. You don't have to know any specific ABI at all. Just knowing like C uses a stack and the system call interface uses registers, good enough for that. And then we saw how to explore system calls with strace. Strace will be your friend. If you get nothing out of this course, you will get just strace everything if you don't know what the heck's going on. Or if it's really slow or whatever, you can strace it and you can get some idea what it's actually doing. Then we saw some different kernel architectures that shifts what runs in kernel mode. So that's it. Just remember, pulling for you. We're all in this together, and have a good week.